In this video, I'm going to talk about the Hamiltonian operator. This video is part of a playlist on quantum mechanics. You can find the link to this playlist in the description below. First of all, let's have a look at what the Hamiltonian is in classical mechanics. So in classical mechanics, the Hamiltonian for one particle moving in one dimension is going to be of this form. So we're going to have h representing the Hamiltonian is a function of x and p. Now, in general, you can actually, in Hamiltonian mechanics, we tend to put q over here, as that's some kind of generalized coordinate, because this doesn't have to be x. But I'm dealing specifically with one-dimensional motion. So I'm going to use x over here, right? This is just one-dimensional linear motion along a straight line universe that extends from minus infinity to plus infinity. So that's, the Hamiltonian is a function of x and p in this case. So this is going to be of the form p squared over 2m. That's the kinetic energy, plus some potential energy function that just depends on x. Now, we could have some kind of a weird potential energy function that is a lot more complicated, but we're going to stick to simple potential energy functions that just depend on where you are. So where that particle is determines the value of v. That's the only thing that determines the value of v. So it doesn't matter how fast it's going at that point, it's just its location. So this over here is actually the total energy of the particle. In classical mechanics, this is the total energy. It's the kinetic energy plus the potential energy. Now, let's translate this into quantum mechanics. So a lot of the intricate mathematical relationships in Hamiltonian mechanics actually get preserved when you go into the quantum revolution. When you go from classical mechanics to quantum mechanics, a lot of Hamiltonian mechanics and those types of ideas are still valid. So let's go ahead and redefine this and put this into quantum mechanics. So the Hamiltonian operator, I'll write it with a little hat on top, Hamiltonian operator is linked to the total energy. So it's like an operator that is linked to all the energy that the particle has. And that has a kinetic energy component, and it also has a potential energy component. Before I write this, I'm just going to put it in the top little corner over here. The momentum operator, p hat, is equivalent to h bar on I times d dx. So I'll just put this in a little box at the top, just so we know where a lot of these expressions came from. So in the previous videos in this playlist, we actually derived an expression for the kinetic energy operator. And that was linked to this form of the kinetic energy from classical mechanics, this p squared on 2m. And what we're going to do is we're going to use that form from the previous videos, and we're going to put it over here as the kinetic energy term. So I just want you to be aware that this actually comes from the momentum operator. So the first bit, the kinetic energy term, is going to have a minus h bar squared over 2m, and then it's going to have a second derivative with respect to x. And this is a partial derivative, not a total derivative, because there could also be other variables that this depends on, right? This is an operator that acts on a function. That function could depend on time as well. But we're just differentiating with respect to x over here. So then we're also going to need this little potential function. And the potential function I'll put over here. That's v as a function of x. So we have something that relates to the kinetic energy. Right, kinetic. That's the kinetic energy, the energy of motion. And we have something that relates to the potential. And the potential only depends on x. So we have the kinetic energy and the potential energy. So what we're going to do in the next video is we're actually going to link this to the time-independent Schrödinger equation. So remember this formula, because this is actually how we define the Hamiltonian operator. But a special little clarification I want to make is that this is only for one dimension and for one particle. It gets a little more complicated when you start bringing in different dimensions. If you have a three-dimensional case, you're going to have several versions of this term, right? One version is going to have an x, you're going to have a y, and then a z. And it's going to be a little more different if you use polar coordinates or spherical coordinates in higher dimensions. So this kinetic energy operator is just the kinetic energy operator for one-dimensional motion for one particle. And this potential is only related to the position of one particle. So that's a very important nuance in this definition. But for our purposes, for 1D quantum mechanics with just one particle, this Hamiltonian operator definition will do. So make sure you watch the next few videos in this playlist and all the videos in this playlist. You can find them all by clicking over here.